Near future of new trends. Latest trend in visualization aims to furnish the illusion of depth in an image by presenting two offset images separately to the left and right eye of the viewer. The brain is then able to combine these two-dimensional images and a resulting perception of 3D depth is realized. This technique is known as stereoscopy or 3D imaging. Three are the main techniques developed to present two offset images: one for eye, the user wear eyeglasses to combine the two separate images from two offset sources, the user wear eyeglasses to filter for each eye the two offset images from a single source, the user's eyes receive a directionally splitted image from the same source. The latter technique is known as AutoStereoscopic, and does not require any eyeglasses. An improvement of the refers of auto-multiscopic, AM, displays which can provide more than just two views of the same image. So, the as realized by AM displays is undoubtedly one of the really new frontier that must be considered for the near future to realize the illusion of depth, since leaves aside the uncomfortable eyeglasses and realizes a multi-point view of the same image. In such a way the user has not only the illusion of depth but the illusion to turn around the visualized object just moving his/her head position with respect to the source. The feeling a sensation of present in a VR scene is a fundamental requirement, and the AM displays go in that direction. So, we want here to present the aleoscopy display that is one realization of such technology, with which our research group is involved in. The movements, the virtual interaction with the represented environment and the use of some interfaces are possible only if the user feels the space and understands where all the virtual objects are located. But the level of immersion in the AR highly depends on the display devices used. Strictly regarding the criteria of the representation, a correct approach for the visualization of a scenario helps to understand the dynamic behavior of a system better as well as faster. But an interesting boost in the representation comes, in the latest years, from a 3D approach which offers help in communication and discussion of decisions with non-experts too. The creation of a 3D visual information or the representation of an illusion of depth in a real or virtual image is generally referred as stereoscopy. A strategy to obtain this is through eyeglasses, worn by the viewer, utilized to combine separate images from two offset sources or to filter offset images from a single source separated to each eye. But the eyeglass-based systems can suffer from uncomfortable eyewear, control wires, crosstalk levels up to 10%, BOSS, 1993, image flickering and reduction in brightness. On the other end, AutoStereoscopic, is the technique to display stereoscopic images without the use of special headgear or glasses on the part of the viewer. Viewing freedom can be enhanced, presenting a large number of views so that, as the observer moves, a different pair of the views is seen for each new position, tracking the position of the observer and update the display optics so that the observer is maintained in the autostereoscopic condition, Woodgate et al., 1998. Since autostereoscopic displays require no viewing aids seem to be a more natural long-term route to 3D display products, even if can present loss of image, typically caused by inadequate display bandwidth, and crosstalk between image channels, due to scattering and aberrations of the optical system. In any case we want here to focus on the as for realizing what we believe to be, at the moment, one of the more interesting 3D representations for VR. Current autostereoscopic systems are based on different technologies which include lenticular lens, array of magnifying lenses, parallax barrier, alternating points of view, volumetric, via the emission, scattering, or relaying of illumination from well-defined regions in space, electro-holographic, holographic optical images are projected for the two eyes and reflected by a convex mirror on a screen, and light-filled displays, consisting of two layered parallax barriers. Schematizes current autostereoscopic techniques. C. Pastor and Watking, 1997, Warner, 1999, and Okoshi, 1976, for more detailed descriptions. Schematization of current autostereoscopic techniques. Our efforts are currently devoted respect to four main aspects. User comfort. Amount of data to process. Image realism. Deal with real objects as well as graphical models. In such a view, our collaboration involves the Aleoscopy Company, www.aleoscopy.com, regarding a patented 3D visualization system which, even if does not completely satisfy all the requirements of a full immersive VR, remains one of the most affordable system, in terms of cost and quality results. The 3D monitor, offered by the company, is based on the standard Full HD LCD, and its feature back 8 points of view is called multi-scope. Each pixel of the LCD panel combines the 3 fundamental subpixel color, red, green and blue, and the arrays of lenticular lenses, then lenticular imaging, see the schematization of, cast different images onto each eye, since magnify different point of view for each eye viewed from slightly different angles, see. A. LCD panel with lenticular lenses, B. 8 points of view of the same scene from 8 cameras. This results in a state-of-the-art visual stereo effect, rendered with typical 3D software such as 3D Studio Max, www.autotatus.it/3dsmax, Maya, www.autotatus.com/Maya, Lightwave, www.newtek.com/lightwave.html, and XSI, www.softimage.com. The display uses 8 interleaved images to produce the AutoStereoscopic 3D effect with multiple viewpoints. We realize 3D images and videos, adopting 2 different approaches for graphical and real model. The graphical model is easily managed thanks to the 3D Studio Max Aliascopy plugin, which is not usable for real images, and for which it is necessary a set of multi-cameras to recover 8 viewpoints, see. The 8 cameras with, A. more or, B. less spacing between them, focusing the object at different distances. The virtual images or real captured ones are then mixed, by means of OpenGL tools, in groups of 8 to realize AutoStereoscopic 3D scenes. Particular attention must be paid in positioning the cameras to obtain a correct motion capture of a model or a real image. In particular, the cameras must have the same distance apart, 6.5 cm is the optimal distance, and each camera must see the same scene but from a different angle, see. A. Schematization of the positions of the cameras among them and from the scene, B. The layout we adopted for them. Reports screen captures of 3 realized videos. The images show blur effects when reproduced in a non-autostereoscopic way, as it happens in the figure. In particular, the image in C reproduces 8 numbers, from 1 to 8, and the user C, on the S monitor, just 1 number at time depending on his/her angular position with respect to the monitor itself. Sum of realized images for 3D Full HD LCD monitors based on lenticular lenses. Representation of, A. virtual and, B. real object, while the, C. image represents 8 numbers seen 1 at time by the user depending from his/her angle of view. The great advantage of the systems consists of an immersive experience of the user, with unmatched 3D pop-out and depth effects on video screens, and this is obtained without the uncomfortable eyewear of any kind of glasses. On the other end, an important amount of data must be processed for every frame since it is formed by 8 images at the same time. Current personal computers are, in any case, capable to deal with these amount of data since the powerful graphic cards available today. Cutting-edge display technologies have brought us many new devices including thin and high-quality TVs, touchscreen phones and sleek tablet PCs. Now the latest innovation from the field is set to the transparent technology, which produces displays with a high transparency rate and without a full-size backlight unit. The panel therefore works as a device's screen and a see-through glass at the same time. The transparent displays, TDs, have a wide range of use in all industry areas as an efficient tool for delivering information and communication. These panels can be applied to show windows, outdoor billboards, and in showcase events. Corporations and schools can also adopt the panel as an interactive communication device, which enables information to be displayed more effectively. From research groups of Microsoft Applied Science and MIT Media Lab has been developed a unique sensor OLED, organic light emitting diode, transparent technology. It is the base of a see-through screen. A Kinect-driven prototype desktop environment by the Microsoft Applied Sciences group allows users to manipulate 3D objects by hand behind a transparent OLED display, www.microsoft.com/appliedsciences. Again from Microsoft Research comes the so-called Hollow Desk, for direct 3D interactions with a situated see-through display. It is basically an interactive system which combines an optical see-through display and a Kinect camera to create the illusion for the user to interact with virtual objects. The see-through display consists of a half-silvered mirror on top of which a 3D scene is rendered and spatially aligned with the real world for the user who, literally, gets his/her hands into the virtual display.